record this talk, and thank you very much.
Perfect. Thank you so much for having me. I'm excited to be here tonight to talk to you all about cryovolcanism and some of the work that I'm just starting to get into right now. So I'm going to share my screen and get started. Okay, everybody can hear me okay? Just give a thumbs up or some kind of sign. Cool. Okay. I'm going to assume that it's working. Cool. All right. So hi, good evening, everyone. And thank you for those who responded in the chat. I see it now. All right. So yes, I'm going to talk to you tonight about cryovolcanism in the solar system and beyond, which I consider the coolest geological process. So before we dive in, I wanted to give you just a little bit of background on who I am. I am a postdoctoral management program fellow at NASA Goddard Space Flight Center, which means that half of my job is actually doing NASA management work, and the other half of my job is doing science research work. And this is one of the things that I research is cryovolcanism. I got my PhD at Arizona State University, and luckily it was pretty close to Flagstaff, Arizona, which is actually going to come up in the talk a little while later. So I study all kinds of things, mostly icy bodies and water in the solar system and different exoplanetary systems. So that's most of my expertise. And if you have questions on anything like Europa, asteroids, Sharon, I'll talk about that a lot today, feel free to ask me at the end of the talk. In general, I like being outside and exploring. It's one of the reasons I got into geology in the first place. So I am doing something a little bit different. I'm not going to be talking about just astronomy today. I'm going to be talking about the geology of the solar system and its geomorphology and how that relates to the different kinds of astronomy work that we can see in the future. All right. So what exactly is cryovolcanism? The strict definition is that it is the eruption of water, ice, and dissolved volatiles onto a planetary body's surface, or pretty much what you'd expect if you ever heard the words ice volcano. And what's really interesting to me about cryovolcanism is that it's present in so many places in the outer solar system, which is the area beyond the asteroid belt between Mars and Jupiter. The problem is we actually don't know all that much about it. For something that's so widespread, for such a massive and major geologic process, there are many unanswered questions about it. And I found that very compelling when trying to figure out what to study. So I've already alluded to this, but there are many questions about cryovolcanism. Specifically, how does it work on different planetary bodies? I've said that it is present in a lot of different places. However, all of these different places have different features of what we think are cryovolcanic structures. So why are they different and how did they get there? And how does cryovolcanism even work? These are still unanswered questions. But thanks to the New Horizons mission that went past the Pluto-Charon system in 2015, we have the best opportunity to study cryovolcanism on one of these ocean or ancient ocean worlds, which is Pluto's moon Charon. But you know, I think I'm getting a little bit ahead of myself here. Perhaps we should talk about regular volcanism first. So, what is volcanism? Volcanism is, in effect, a planet's way of removing heat from its interior. That is exactly what drives volcanoes here on Earth, and it drives volcanism in other planetary bodies as well. We'll see a lot of different examples of that. And volcanoes are present on most of the solar system's planetary bodies that are relatively large, as in more than 600 miles in diameter. Probably should have kept everything in kilometers. This is a science audience, but it's in miles and kilometers, so sorry about that. So what's interesting about volcanism, I guess one of the things that's interesting about volcanism is that the eruptions are driven by pressure and buoyancy. Liquid rock is less dense than the solid rock that it rises through, which allows for eruptions to happen in the first place. On Earth, this makes a lot of sense. On other planets, this also makes a lot of sense because it's just a matter of buoyancy versus gravity. Different planets having different gravitational pulls can affect the force of gravity, which is part of the reason why eruptions on different planets look so different. There are many other factors at play, and we'll go over those. And the reason I'm giving you such a fundamental background on this topic is because I want you to understand when we go and talk about cryovolcanism, just how different it really is. Volcanoes on Earth do tend to happen around the plate boundaries. So the plate tectonics is the theory that Earth's crust is broken up into different plates, and these plates move around because of shifts in Earth's mantle and the asthenosphere. So all of these plates moving around cause a lot of friction, and that friction leads to heat. How do planets get rid of heat? Volcanoes. That's why so many plates are so volcanically active. There is a pretty strong correlation, but it's not 100%. Of course, there are lots of hotspot volcanism areas, such as the Hawaiian Islands and even Flagstaff, Arizona. I've actually walked up a couple of these different volcanoes in Flagstaff, and thankfully, Flagstaff has mostly dormant volcanoes, but it's interesting to see what these features actually look like up close. And humans have lived around volcanoes for millennia, potentially since humans were even walking the earth, despite their dangers. Of course, we saw this fairly recently with the Tonga eruption in the South Pacific. So unfortunately, I won't be able to answer many questions about that. I think there are still so many unknowns about that eruption in the first place. But it's definitely a great example of how destructive volcanoes can be. The most destructive eruption that I can think of actually happened about 252 million years ago with the Siberian traps in Russia. It's something called a large igneous province. It actually spewed out so much magma, so much basalt and toxic fumes that it caused the Permian mass extinction when 95% of life on Earth died out. So volcanoes are hugely important for the history of life on the planet and also the geologic history of the planet. But volcanoes on other planets, of course, don't look exactly the same as they do here on Earth. What we have here in the biggest picture to the left is the biggest volcano in the solar system. It's called Olympus Mons. It's on Mars. It's about 13.5 miles tall and 370 miles wide. It's absolutely enormous, and it's incredible to think that a planet as relatively small as Mars has the largest volcano. It's fascinated many a planetary scientist. But we also could go over to Venus, which is this more orange picture in the middle here. And these are lava flows. They're called pancake volcanoes because they are relatively flat. So these pancake domes are actually great evidence for recent volcanism on Venus. They're about 16 miles across and only half a mile high, despite the fact that Venus is a larger planet than Mars. You might think it just has more stuff to erupt. It's also a much hotter planet. What's important about these pancake domes and the extensive volcanism that was present on Venus at one point is a lot of the gases that came out from volcanism have now become integrated into Venus's atmosphere. So studying Venus's atmosphere is a clue about what was in Venus's interior many millions of years ago. And finally, we have in this bottom right-hand corner, we have Jupiter's moon Io, which is the most volcanically active body in the entire solar system. The GIF that you're watching here is of its famous volcano called Tvashtar. The plume that you see is 200 miles tall. So it's enormous compared to the size of the planet. So how does a moon that relatively small have such an active volcanic history? There are many things that control volcanism. I've alluded to this before. There are the specific properties of the magma itself, like the temperature, the density, the viscosity, or how sticky the magma is, how well it can flow. Dissolved gases, which can change the viscosity, the water content, the crystal content, and the bubble content. All of these different pieces are related to each other, making it fairly difficult to model. There's also the eruption properties of the volcano itself. On Earth, it could be something like its elevation. There's also the eruption rate, so how quickly magma and lava spill out. It could be something like ash and gas and dust as well. The eruption volume, just how much a volcano has to give. The number of different eruptions, does it just erupt once like it does in Flagstaff, Arizona, or is it something more continuous like Kilauea on Hawaii? The number and size of vent openings as well, just how many places on this volcano is lava coming out. When we talk about planetary volcanism, though, what we most care about, or at least what we think is most relevant, are the different planetary variables. So things like gravity, atmospheric pressure, and the fact that there is an atmosphere. This is part of the reason why the pancake domes on Venus are so flat, is that pressure from the atmosphere is just pushing down the lava, and it can't rise, it just goes out because it can't go up. The bulk composition of the actual planet, so that determines what the composition or the most likely composition of the magma is going to be in the first place. And then perhaps most critically, we have to talk about the heat budget of a planet as well, because that drives how volcanically active a planet is, because again, volcanism is the way that a planet releases heat. So what are these heat sources and where do they come from? The first main planetary heat source is that of accretion. So when a planet is just forming out of the gas and dust in a protoplanetary disk, like what we see in this picture here, these rings are a sign of a planet forming, that accretion energy is the first main source of heat on a planet. But it's not the only one, because as soon as you go from something like a little dust bunny in space and you eventually just accrete enough dust and other gas, and eventually you have a planetesimal, you have more, and it grows into an actual planet. Then when the planet gets to a big enough size, you start to generate heat from differentiation, or the process of forming layers and moving mass around within a planet. This is a really neat animation that I found about what differentiation can look like. It usually does happen from an inside out kind of pattern. But if you look really closely at the end, you'll see that there's a very thin strip of orange, and that actually represents a magma ocean. So magma oceans were literally what they sound like. It's a layer of molten rock underneath the surface that spans what could be the entire planet. So we want to say that on places like the moon definitely had a magma ocean. I think the Earth might have as well. I don't know if it was as extensive as the one on the moon, but it turns out magma oceans could be an important part of planetary differentiation that we're just starting to consider now. The third main planetary heat source is radioactive decay. So this comes from something like uranium decay in the core, and as it decays, it's letting off heat. That heat is generated in the core and it makes its way out of the core through convection and radiation. It finally makes it up to the surface, where it comes out as heat in the form of a volcano or something like a mid-ocean ridge, which would be a different kind of plate boundary. And then finally, there's one called tidal flexing. And we're going to focus on this one a lot because it is the most important heat source in the outer solar system. So I've already said the punchline here, but the most important heat source in the outer solar system is tidal flexing. And tidal flexing refers to how a planet is actually warped as it moves through a very strong gravity field. Something like the Galilean satellites going around Jupiter is an excellent example of tidal flexing. So the 4 Galilean satellites are the ones that we see at the top in order from left to right. They are Io, the most volcanically active moon in the solar system. And then there's Europa, Ganymede, and Callisto. Io's high volcanic rate is actually driven by the fact that it is the closest moon, closest one of these moons anyway, to Jupiter, and it orbits so quickly around an object so massive as Jupiter that it's constantly changing its own shape. And all of that movement creates friction. The friction leads to heat. The heat is released through volcanism. And that's why Io is so volcanically active. Europa, on the other hand, not exactly as active as, not volcanically active anyway, as Io, but it is still being flexed. So its surface moves about plus or minus 30 meters, which is plus or minus 100 feet. That's quite significant. Every time it orbits, so it orbits Jupiter every 3 days. So every 3 days, its shape is moving by plus or minus 100 feet. That's a lot of heat, and it's part of the reason why Europa is able to sustain a global ocean underneath its relatively thin ice shell. Okay, so now that we have a good understanding of what volcanism is, let's talk about cryovolcanism. So the first one I want to talk about is the one that's actually closest to us. It's on a dwarf planet in the asteroid belt called Ceres. So Ceres is a dwarf planet. It was visited by the Dawn mission that actually orbited Ceres between 2015 and 2018. And technically Dawn is still at Ceres. It's kind of stuck in this orbit because its fuel ran out. Don't worry, it was supposed to. But so the mission is just kind of hanging out there. It's not actually doing science, but it is still there. So one of the things that it found on its reconnaissance of Ceres is that it has a mountain, its most prominent mountain called Ahuna Mons, which is a relatively young mound. It's only estimated to be about 240 million years old. But the best evidence that we have says it's actually a cryovolcano. And if it is, then it is the one that is closest to the sun in the solar system yet discovered. That's a pretty big deal because we're trying to figure out what the limits of cryovolcanism is, what kind of activity and what are the conditions under which it needs to happen. Ceres is a very important clue for that. So one of the reasons we think that cryovolcanism might be possible on Ceres, despite the fact that it's a dwarf planet, so it's not as big as something like the Earth, but it's still active. Oh, and it's also not around something like Jupiter, so it's not around something as big. So it might still have its own unique heat source, perhaps from something like radioactive decay. And part of the reason why cryovolcanism might be possible is because of the presence of a salt called ammonia. So I don't know how many of you drive, but I'm sure you've noticed that we have gotten snow in the region in the past couple of days, and maybe not a lot of it. But one of the preparations that that people do to prepare for snow is they put salt down on the roads. And the reason we do that is because salt lowers the freezing point for snow, which is mostly water. So adding salt to a water-based mixture will actually keep it liquid for longer, which makes it a lot easier for something like cryovolcanism to happen because the cryomagma is it's better at flowing. Moving on out of the asteroid belt and into Jupiter's orbit, we should talk about Europa. This is the one that I actually did my dissertation on, so I could talk for an hour about Europa itself. I'm going to try and restrain myself from doing that today. But Jupiter's moon Europa, is the perfect example of an ocean world. I've already talked about how it has an ocean underneath its thin ice shell. That is mostly sustained by the heat that comes from tidal flexing. But Europa, to give you a sense of scale, is about the size of our own moon. And the ocean that is underneath this ice shell is salt water of some kind. So again, we see the presence of salts playing an important role in our solar system and potentially in some of the cryovolcanism that happens on Europa as well. So the picture that you see to the right of the text on this slide, all of that red gunk, that is a salt. We don't know exactly what kind of salt. It's actually really tricky to figure out precisely what it is. And some of that is actually pollution as well from Io. All of its volcanic activity spitting out sulfur, it ends up hitting Europa. So, it's kind of rude, but helpful in terms of science. So when we look at this, the red stuff, the red salt, it gives us a clue that the surface is somehow in contact with the ocean underneath. And that's a big clue that there's something happening. There's some kind of material transport going on. So again, we talked about how Europa orbits Jupiter every 3 days. That tidal flexing is that main source of heat. How does heat help get stuff to the outside? Well, one of the clues that we have, and one of the clues that I focused on during my dissertation, are these very small features called microfeatures. They are these, they're endogenic, so they're created by Europa. These small features that are less than 100 kilometers squared in area. So planetary geologists, including me, we don't fully understand how they form. There are many different theories, and some of them, they make different predictions, but we don't have the imaging required to differentiate between those predictions just yet. But one of the major features of one of the models is that one of the major implications is that these features could be related to each other through some sort of continuous process. And perhaps that continuous process is cryovolcanism. For example, in this hybrid feature that is towards the bottom left, so it's this one right here, I hope you can see my screen, but it's the one that says hybrid on it. Notice that the orange circle, it has what looks like a dome or some kind of raised feature in the middle of a moat of some kind. And it's actually called that in the literature, by the way. It's called a moat. So is this evidence of a cryovolcanic dome? And is the moat actually cryovolcanic outflow? There's a mission called the Europa Clipper that will launch in 2024. It will arrive at Europa in 2030, and maybe we'll start to get some more answers then. Moving away from Jupiter, now we're going into Titan, into the Saturnian system, the biggest moon of which is Titan. We'll talk about that too, but we can't forget Enceladus either. So Enceladus is one of the smaller moons of the solar system, but it is an ocean world, and it is very active, especially at its south pole in an area, in a region called the Tiger Stripes. It actually has geysers coming out of it almost nonstop. So could this be an example of explosive cryovolcanism in our solar system? And then moving on to Titan, where we have one of the best examples of cryovolcanism in the entire solar system with a with a cryovolcano that has an awesome name called Doom Mons. So I don't know why there haven't been any science fiction movies set at Doom Mons, but it seems like it would be a perfect place for an excellent movie. It's almost a mile tall, actually, which is incredible to have something that big. It's 37 miles across. And all we have so far are pictures. We would like to get more pictures, of course. We'll have to wait a little while for another mission to go out to the Saturnian system. But if we do so with a better understanding of cryovolcanism and we know what to look for, maybe we are going to learn a lot more about Doom Mons the next time we go out there. We can also talk about cryovolcanism at Uranus and Neptune's different moons. Unfortunately, these were visited very briefly by the Voyager 2 mission. So in 1986 for the Uranian moons, and then in 1989 for Triton, which is Neptune's moon, or one of Neptune's moons. And we have no idea how these moons have changed in the past, 35 years. We just don't know. So we would love to see another mission go out there just to see what has changed and see if there's any active cryovolcanism happening this far out in our solar system as well. So again, these are just a lot of examples of places where we have seen cryovolcanism in the solar system. So we know, and it's well established that this is a process that is happening. But there are still some fundamental questions that we have. So one of the biggest is that when we talked about volcanism on Earth, we established that in a large part it works because the liquid rock is less dense than the solid rock, which allows it to rise to the surface fairly easily. That doesn't exist with cryovolcanism. Liquid water is actually more dense than solid water or ice. So how could water, say from Europa's ocean, make it to the surface where it would have to travel through, let's say, 10 kilometers worth of ice? How the heck did that happen? The only answer that makes sense is that there's some kind of pressure pushing it out that is strong enough to counteract the force of gravity that would otherwise hold it down. But what does that look like on other worlds that aren't just Europa? This is still a big outstanding question for a widespread process like cryovolcanism. But another question we have is, what exactly is a typical cryomagma composition? What does it look like? What is it made out of? How sticky is it? How many gases does it have? What is its crystal content? All of the questions that we would have for a normal magma on Earth, we would have for cryomagma, except we don't have a lot of information about what that looks like. How much cryolava could be released per flow? Not sure. How often can cryovolcanism happen on a world? Again, not sure. So for a process that is so widespread, some big questions still remain. So how the heck are we going to get any kind of answers? Oh, right. Oops. I got ahead of myself a little bit, but yes, so cryovolcanism is a fundamental process that we do not fully understand. And yet, if we are going to understand and figure out the history of the outer solar system, this is an important detail that we need to understand a lot better. So, luckily, the New Horizons probe went to Pluto, and I have to say, I was personally very surprised by what they found out there, what the mission found and what the team found, but it's really incredible because it turns out the Pluto system with Charon and all of Pluto's moons might be the key to unlock the systems, to unlock the entire outer solar system's cryovolcanic history. So what we have on the left is a picture of the New Horizons probe. It's about the size of a baby grand piano or a small car. And it was, at the time, it was the fastest moving man-made object that was traveling through the solar system. And even though it launched in 2006 and it was going faster than anything else, it still didn't reach Pluto until July 14th, 2015. It was quite a long journey, actually, and it had to be done just right because of Pluto's relatively wonky orbit. But it did make it to Pluto, and that's what we have in the middle is, of course, the famous heart on Pluto's surface. And what we have on the right is different maps of the different types of ices that are present on Pluto's surface. So what we have up here with the CH4 in the purple in the top left, that is methane ice. The N2 is nitrogen ice, that's in the top right. Bottom left is carbon monoxide ice, and then the bottom right is water ice. So interesting to see the different patterns of these ices on its surface. That's certainly a clue for what happened and how Pluto came to be the way it is. But I'm going to talk to you mostly about Pluto's largest moon, which is Charon. This is actual imaging of Charon's surface. Now you'll notice that we don't see all of it particularly well. We only have about 40% of it imaged at all. And that's what we're looking at here. But I'm going to call your attention to this big scarp, this cliff actually, that goes kind of through the middle here. You might have to look a little closely to see it, but once you see it, it's hard to miss it. It goes right through here and up the middle. It's almost like a scar that goes across Charon. And this one feature is very indicative of, it turns out is very indicative of cryovolcanism. So some basic information on Charon first is that it's about 750 miles in diameter, or about 1,200 kilometers, and it co-orbits with Pluto. So Pluto and Charon kind of co-orbit each other. They both revolve around a center of mass that isn't in one body or the other. That's unusual because most moons revolve around a planet and that center of mass of the entire system is within the planet. Not so with Pluto and Charon. And that again, they're both exerting tidal flexing on each other because they're not exactly the same size. Charon is definitely smaller, but the fact that they are so similar in size means they're both affecting each other in terms of that heat budget that we talked about earlier. Its overall, Charon's overall density suggests that its interior is a mixture of ice and rock and very likely differentiated. So that's another source of heat that we suspect was present on Charon. And maybe it's not actively differentiating anymore, but the fact that it happened at all is a really good clue that cryovolcanism might be possible. We also noticed that Charon's surface is dominated by water ice and about less than 10% or equal to 10% ammonia bearing ices. So again, we have that slight salt content that might have lowered the freezing point of the water ice that could have allowed cryomagma and cryolava to flow. But what are some of the geomorphic evidence or the shapes of features on Charon's surface that suggests that cryovolcanism might have happened. So first, remember when we looked at the big map of Sharon and there was that scar-like feature that went through the middle? To the north of that is a land called Ozterra, which is rugged and it's dominated by fractured block surfaces, and it has these deep troughs between these blocks. So that's pretty telling that there was some kind of extension feature. So I'm going to talk to you about that right now. And if I can ask you to look at me and not look at my slides, I'm going to show you a little demonstration. So if we had something like a divergent plate boundary, so something that was caused by two plates being forced apart, what would happen is that the land in between them would start to slide down, and it would create a geomorphic feature called a graben, which is a fancy name to say a trough, where it's some kind of valley, but it's specifically formed by tectonodeformation, or plate tectonics being pushed apart. So if we see that happening on Sharon, which we think we do, that indicates that there was some kind of extensional force pushing parts of Sharon's surface around. Hang on to that fact, because we are going to come back to it. To the south of that scar that we saw on Sharon, we see Vulcan Planitia. Vulcan Planitia is a relatively smooth area. It's still cratered, as is Ozterra, but it's cratered slightly less. What's also telling about it is that it's on average 1 to 2 kilometers lower in elevation than Ozterra. So we already have this lower area where if there was cryovolcanism and it did flow like water at some point, it would have wanted to collect in a lower elevation area. So again, we know that Vulcan Planitia is slightly less cratered. That indicates that it's relatively young compared to Ozterra, but both of these areas are estimated to be about 4 billion years old, judging from the crater records. Oh, but wait, there's more. There is more evidence of cryovolcanism on Sharon. Now, remember when we talked about those hybrid features on Europa that have that little moat? We see similar features actually going on Sharon. We have Clark Mons over here and Kubrick Montes on the right. These are in the little blue boxes. And these kind of look like those elevated domes or elevated features surrounded by a dark moat. It's a little more obvious in Clark Montes, which is over here. You can actually see that there are potentially multiple mounds that seem to be linked together by a giant moat of kinds. They are clearly elevated features. They rise above the surface by quite a couple of miles, 2.5 to 3 kilometers. So that's like a mile, 1.7 miles at most, 3.7 to 4, like 2.5, no, 2.3, something like that. So that's another piece of evidence. What we have on the right actually is pitted terrain. And we're not 100% sure what this is or how it formed. But we wondered, looking at that, is if it was a cryovolcanic flow and there was some kind of gas trapped in the cryo lava that once it reached the surface, it was able to release itself. Maybe it froze in place. So maybe these pitted terrains that we see is evidence of gas escaping from the cryo lava. So these are just ideas. They're compelling ideas, and the trick now is to figure out exactly what happened. So there are some fundamental questions of Sharon now that we've looked at this. That Vulcan Planitia is covered with this relatively smooth material made up of ice and ammonia. So yeah, it makes sense that it's a massive cryovolcanic flow. Now, how did this cryovolcanic flow happen? Remember how we talked about the graben that would form, those big troughs? They are caused from extension of Sharon's shell or crust. So we think that that extension might have happened because there was a subsurface ocean on Sharon that might have been generated by all that heat from its initial differentiation that eventually froze. And as it froze, it expanded. Something like, if an ocean had between 15 and 30% of Sharon's entire volume, when it froze, and if it expanded by about 7% based on the amount of ammonia that was present in it at the time, it would have caused an extensional strain that would have increased Sharon's volume by about 1 to 2%. So that is what would have caused that extension, that pressure going out and actually causing some of these grabens. So these are numbers that were estimated by other researchers, and we looked at this and we said, I wonder if there's something there. Unfortunately, there is some inconsistent timing between the ages that we get from the crater counts of 4 billion years compared to what we get when we try to model cryovolcanism beginning on the surface. And what we have is that even with the crater age estimates, which have error bars of, no joke, plus or minus 1 billion years, it's still not enough to overlap with the error bars of the estimated onset of cryovolcanism. So here on the right, this circle represents the crater age estimates. What we have, or sorry, on the left, that estimates the crater age. And what we have on the right is that models the time of Sharon's ocean freezing that would have led to the extension event that would have led to cryovolcanism. So we look at this and we say, that's a gap in our knowledge. We should probably figure that out. So we put in a proposal to NASA to answer this question, and it got funded. Oops. I forgot to animate that part. All right, well, part of what we're doing is a whole lot of modeling. We have to figure out what Sharon's exact heat budget is. Again, it co-orbits with Pluto, so we need to take that into account. There's a lot of different parameters that we need to account for when we do this kind of modeling, and they interact with each other in different ways. So we have a special code called Icy Dwarf that actually can study the interior evolution of Sharon over time, and we can see if we can match cryovolcanism's onset to the age of the craters, or if maybe there's no way to do it and maybe the crater ages are wrong. That would be a pretty interesting finding as well. What we can also do with Icy Dwarf that we can't have done before without this code is that we are now able to estimate the volume and the composition of the cryolava that would have been able to flow out onto the surface. So we can compare our models to what the New Horizons mission actually looked at, and we can see where they line up. Another thing that we can do is, of course, we can look at the New Horizons mission data itself, mostly in the form of imaging, and we can try to constrain the volume of a potential cryovolcanic flow. And we can do that by looking at how many craters are present on the surface. If there were craters there before, and the cryolava flowed out, some of those craters might be buried. So by looking at the areas represented by these stars, which are these lower density areas, we can figure out if there were multiple vents for cryovolcanism. We can try and estimate its volume, its depth. We can get a lot of different parameters just by looking at the data itself. And then finally, once we've done that, because that's not simple to do. It sounds like only two things, but there's a lot of work that goes into both of them. But once we've talked about it, and once we've looked at the findings from both of these, we can put them together and we can see if we can apply it to other places in the solar system, like those we've talked about before. Not only Sharon, but things like Uranus's moon Ariel, which is shown to the right of the screen. And then once we can do that, we can start to understand how cryovolcanism works, not just on Sharon, but on other places in the solar system as well. And I have to acknowledge the team here doing this work with me because they are really phenomenal. Like, if I could put together a dream team, this is exactly the team that I would do. Steve Desch, who is the PI, there's Kelsey Singer, Mark Navu, and Lene Quick, and they're all experts in outer solar system, cryovolcanism, cratering, you name it, they do it, and they're really fantastic. You might have also noticed that a lot of the places that I mentioned that are cryovolcanic hotspots of the solar system are also ocean worlds, especially something like Europa and Enceladus, and even Titan to an extent. But what is an ocean world? So an ocean world is a terrestrial planetary body that contains a substantial amount of water as part of its hydrosphere, either on its surface like we have on Earth, or as a subsurface ocean like on something like Europa or Enceladus. The connection between ocean worlds and cryovolcanism is almost a perfect circle, if it was a Venn diagram, because, or it should have been like that, excuse me. And the reason for that is because to have cryovolcanism, you need water in the first place, which means you're already restricting the amount of places where these events can happen. So now that we have this, what does it mean for worlds beyond our solar system? When we talk about, when we talk about the different potentially habitable planets, we talk about planets that are in the habitable zone. And the habitable zone around a star is the region in the distance from a star where the water would be, where liquid water would be stable on the surface of an Earth-sized planet. So for different stars have different temperatures and they have different sizes. So the habitable zones around these stars are going to be different. One of these places, also I should mention though that as stars evolve, just like their planets, the habitable zone can change. It can move in, it can move out. Planets can be in the zone 1 millennia and out of it the next. It all depends on what that sun is doing and if there's any perturbation to the planet's orbit itself. And that's what's going on the right of the screen. We have different scenarios where planets are moving in and out of the habitable zone. So in and out of places where water would be stable and then maybe unstable and then potentially stable again. So aside from the fact that things are happening to the planet itself that the planet is doing, the star around the planet is also getting into the fold. So there's never one thing happening. It's always a mixture of 1,000 things that we need to consider. But one of the most famous planetary systems other than our own is that of the Trappist-1 system, which show 4 different planets actually in the habitable zone. So in that area where liquid water is stable on the surface. This does not mean that these planets are inhabited. Just because a planet is habitable, it does not mean that it is inhabited. So we have to do a lot of work to figure out if there is a biosignature or some kind of unequivocal sign of life. And then there's a lot of, that's an entirely different field to a very intense field to try and figure out exactly what a biosignature is. But we can look at the Trappist-1 system and we can compare it to our solar system. And we notice that it's much closer into its star, but its star is also far less energetic than our sun. So it goes to show you how diverse different planetary systems can be and makes us question what are the limits of things like volcanism and cryovolcanism on some of these worlds as well. Especially considering that exoplanets come in many different shapes and sizes. Well, maybe not so many shapes, they're all pretty spherical from what we can tell, but definitely different sizes and different distances from their stars. To give you an idea of where Earth forms, we would be right there. And if you notice, there are so many different planets that are much, much bigger than Earth, especially these ocean worlds and these ice giants. We don't have good examples of that in our solar system, not even things like Uranus and Neptune. These would be even more different and potentially even a lot more solid than the gas giants that we have out there. Like they could actually be very large rocky bodies. And a lot of the work that people I work with are doing are trying to characterize these planets and try and figure out what they are, what they're doing, and what they might look like on the surface. So again, if ocean worlds and cryovolcanism are linked, then how many exoplanets are ocean worlds? So one of my collaborators, actually, Lene Quick, she led a team that examined 53 of these terrestrial exoplanets between up to 8 Earth masses and up to twice the size of Earth, and considered different forms of heating, again, the radiogenic heat from that, things like uranium decay within a planet, and also the tidal flexing heat generation that we might see if a planet is relatively close to its star. She found, or they found actually, that all of the exoplanets that they studied, all 53, should be either volcanically or cryovolcanically active. That's a really interesting find, 100%. Wow. Even more interesting than that is that up to about a quarter of them could be candidate ocean planets, and 9 of them could be cold ocean planets, so something more like Triton rather than Europa. So we have potentially these cryovolcanic worlds that are constantly recycling material between its interior and its exterior. So what could that mean for life, and just how common are these ocean worlds in exoplanet populations in the first place? So why does this work matter overall. First off, on Earth, volcanic rocks are a way to directly sample Earth's interior, or any planet if we could actually land on the surface and analyze it. Volcanoes bring material up from the interior that we wouldn't otherwise be able to get to. There's no way that we can dig down as far as some of that magma has journeyed from. And the same can be true for cryovolcanism. If we went to somewhere like Europa and we actually landed in what we think is a cryolava flow, we can directly sample the surface. And we can we can directly sample what's on the surface to learn about what is inside of Europa. Especially for something like Venus, volcanoes are also responsible for putting a lot of gas into atmospheres. These atmospheres could be very primitive, or they actually could be very evolved, but something is going on where these volcanoes are constantly interacting with the atmospheres because of all of the gases that they're putting into it. And we can learn a lot about an exoplanet's surface just by looking at its atmosphere if we know to look for the right signals. Volcanoes, along with plate tectonics, they're responsible for cycling a lot of the material that is necessary for life to function. Plate tectonics, especially these subducting plates, they push crustal material down into the interior of the Earth, where they're melted and eventually come back out through the form of volcanoes. And that kind of cycling is important for redeveloping nutrients that life needs to survive and maybe even thrive. So, and again, ocean worlds and cryovolcanism very closely linked. If you want to find life, you should follow the water. Cryovolcanism is a great way to do that. So missions like the James Webb Space Telescope that is currently in orbit successfully, by the way, around L2, which is very exciting. I think commissioning begins either today or tomorrow. So I know we were all holding our breath about James Webb when it was launching and as it unfurled, but it did so successfully. So it's great. And we're going to get a lot more data from exoplanets because of that mission. So, all right, last slide. Here are my final thoughts. That cryovolcanism offers very important clues to how planets and moons of the solar system work and provide important clues for how exoplanets around other suns work. That understanding cryovolcanic processes on Charon is the key to understanding cryovolcanism everywhere in the solar system, or at least in many, many places, more so than we've had before. And that there is still so much we do not know about cryovolcanism, but that I'm really excited to work with the team to figure it out. And I think we're going to find some really interesting things due to certain bureaucratic issues. We haven't actually begun this work yet, despite my best efforts, but we are going to have a great time. And we're going to be so excited to show you results when they are ready. So that is the end of my talk. I've left my email there just in case you have more questions that we don't have time for. And well, with that, I will take your questions.
Hey, thank you. If you wouldn't mind, you can go ahead and share a round of virtual applause using the reaction button on Zoom to thank Dr. Noviello for the excellent talk. I really appreciated that. That was really cool stuff. I hadn't really thought too much about the cryovolcanic processes that might be going on Charon, so that was pretty neat to hear about. All right, so now I'd like to open the floor for questions from the audience. And so we have a couple of questions in the chat, and I'll go ahead and ask those. But if you have more questions in the chat, please go ahead and post them there. The first question comes from Vikram. If this is how planets are formed, then why is Jupiter a gas giant? Sorry for my ignorance, but I was not able to find a good enough source. This is referring to early on in your talk.
No, Vikram, I'm really happy that you asked that question. So this went back to the slide where I was talking about how planets form and how that initial energy from that initial accretion was a main source of heat, especially for young planets. So every star forms in a cloud of dust and gas. And then that cloud of dust, that disk actually of dust and gas, eventually also forms planets because there are little pieces of dust that begin to stick together. More dust sticks together. It's like a giant marshmallow almost that just keeps growing bigger and bigger and bigger and bigger until you eventually form a planet. many planets, especially the planets that were closer to the sun, they were interior to a place, a distance from the sun called the snow line. So within the snow line, there were no volatiles. So a volatile is something that that turns into a gas at a relatively low temperature. And the sun at this point in planet history was so hot that it actually burned off all of the volatiles. But beyond the snow line, that's where more gas was, more of these volatiles. So the terrestrial planets that we have today, Mercury, Venus, Earth, and Mars, these formed most likely interior to the snow line. That's why they aren't gas giants. But if we look beyond the asteroid belt, of course, we have the gas giants. And what we think happened there is that these planets, the planet's core of these gas giants, they actually formed, and then because they were surrounded by all the gas, they eventually got big enough that they had enough gravity to hold onto the gas as well. And then once they started accreting gas, they just got bigger and bigger and bigger. Jupiter also took a tour of the solar system. It kind of wiggled around for a little bit. That's part of the Nice model or the Grand Tack, depending on which one you prefer. So, and I'm skipping over many, many details, but basically that's what happened is that some of these planets formed, got lucky in where they formed, and some of them were lucky that they just got a lot of material very quickly, and and the bigger you get, the easier it is to hold on to more stuff. So it just became this gigantic planet, and that's how we ended up with Saturn, with Jupiter, Saturn, Uranus, and Neptune.
Wonderful, thank you. And we have a hand up from Asian Nice Show, aka Spaceman. I don't know if that was intentional or not, but if you'd like to ask a question, you can go ahead and unmute and ask your question. Maybe. Okay, well, you're still muted, but you can unmute yourself later if you want to ask a question. In the meantime, we have another question in the chat from Aiden. I like this one. It's interesting. How can ice be made up of material other than water?
So ice, almost anything can be a solid. So ice is, or specifically water ice, is just the solid form of H2O. So it's water in liquid form, and it's water vapor when it's in its gaseous form. And we have water ice here on Earth in pretty abundant qualities, which is great, great news, and liquid quality and liquid quantity as well. So we have that, but then as soon as we get to the outer parts of the solar system, again, we're beyond that snow line. The temperatures are very, very, very cold, far enough away from the sun that even things that wouldn't easily condense or turn into solids at Earth temperature and pressure is starting to turn solid. So that's why as we go to the outer parts of the solar system, we see more methane ice, we see more nitrogen ice, we even see carbon monoxide ice on Pluto and Charon. What's really cool about Titan, actually, I'm going to bring that up, is that it is so cold, and also its atmosphere is so thick that it can actually condense methane from its atmosphere into liquid methane. And then it does have a rain cycle, a precipitation cycle, but it rains liquid methane, and it has methane lakes instead of water like what we have here on Earth. So that part just kind of blows my mind. But basically it's like, if it ever got cold enough that even methane could freeze, then you would have methane ice. Can you imagine like methane glaciers? Well, actually, yeah, I can, because they're on Pluto.
Yeah, that blows my mind. I mean, basically, ice is rock. It's just, if you grew up on Pluto, you would always think of ice as rock. But if you saw running liquid water, you'd go, "Oh my gosh, that's lava," but not exactly. But we have different names for different things. But you're right; it's referring to the state of the matter. Great. So Dr. Park said a very smelly moon if we had methane. So we have a fun question earlier. And do you think aliens are real? Because that's kind of related to some of this stuff here. So
definitely. So I'm going to put on my NASA hat here and say that there's a big difference between finding a habitable planet, finding an inhabited planet, and then finding a planet that has the technological capabilities that we might associate or put on par with our own capabilities as humans. So all of those are very different categorizations of things that scientists I work with are looking for. And I said this in the talk, but different biosignatures are incredibly difficult to tease out. There's just so much data that comes from looking at an exoplanet that are it's actually very difficult to tease out exactly what it is. So we're trying to figure out exactly what makes a biosignature in the first place. And then even if we had a biosignature, we would have to try and figure out how much life is there. Is it just, is it a biosignature that would be given off from something like a single-celled organism, billions of them, but just single-cell organisms? Are they multi-celled organisms? Or would we get if we ever got back something like a radio signal that didn't originate from humankind civilization, we might have to assume that is a technosignature or a technological marker of an advanced civilization. So there's a lot to look for when it comes to looking for life outside outside of the solar system. And then even within the solar system, things are very difficult to find. We don't see any evidence of advanced civilizations in our solar system, but maybe on some place like Europa, we will find single cell organisms.
Yeah, no, that's a great answer. So another fun question, which actually I like this question. Could the Earth have been cryogenically active during its ice age?
That is a good question.
I guess another related question is it cryogenically active now?
It's, to my knowledge, no, it is not. I think we're just too warm here. There's too much of this radioactivity coming out of the Earth that we would have to look in some place like Antarctica or the Arctic for any kind of these cryovolcanoes. And I don't think one has ever been discovered. I do think Earth is too warm. I think even during its ice age or its multiple ice ages, I think it was still just a little too warm. Unfortunately, because how cool would it be to just walk up to a cryovolcano and be like, I got this. This is nothing. Unfortunately, we can't do that, not on Earth anyway. I think Ceres is about as close as it could be, but that doesn't mean that places like Iceland aren't absolutely awesome places to visit. They actually have volcanoes erupting under glaciers. So that's a very special kind of geology that we only see in Iceland, and they have wonderful words to describe it, like Jökulop. So I would love to check it out one day.
Yeah, so when you have a geyser like at Yellowstone National Park, that's a different kind of geological process then?
Yes, that would be a hydrothermal vent. So that is formed by a lot of steam underneath. So if you ever go to Yellowstone, you should know you are walking on a super volcano, and there's a big pool of magma underneath your feet at all times, and that is constantly that heat is constantly trying to escape. And one of the ways that it does that is the geysers and the hot springs that are so present at Yellowstone.
All right, thank you. Yeah, so we have a lot more questions. We're at 8 o'clock now. Are you willing to stay with us for a little bit longer during our telescope tour? And we'll be able to ask you a few more questions.
Yeah.
Okay, great. Thank you. And then also, I just want to see, I saw Stephen Dash in the audience. So hi, Stephen. And I guess you work with him at ASU. Okay. Yes. All right. So we're going to go ahead and swap screen shares.
All right. I will stop.
And we're going to start with a view of our observatory. So Kevin, do you want to introduce us to, or introduce us to what we're looking at?
Sure. Hi, everyone. Welcome virtually to the JMU Campus Observatory. The views you're looking at now are on the roof of Research Hall. As you can see, we'll start with the bottom left view. We have the actual observatory dome itself. The weather is holding out for us reasonably well tonight, so we are opening up. So we'll get to see some things using our camera. You can see the shutters open on the left-hand side there. This dome's about 20 feet across or so. and the top can spin all the way around so that the telescope can peek out and look in the sky. As we can see right here, here's the telescope itself. This is a 32-inch rich accretion cast grain reflecting telescope. Now, all those words basically just talk about, they describe the light, the path that the light travels through as it comes from the sky down into the eyepiece or the detector.
Is our dome spinning randomly?
Yes, it appears to be doing so. We've had
it might be looking for the home position. Okay, all right.
We've had quite a number of interesting glitches recently.
Yeah, we could flip back to the other view here so we could just kind of see the dome turning around at the same time.
Sure.
Go ahead or continue.
All right. So how our campus telescope works is the light comes in from the sky, whatever astronomical object we're pointing at, and it comes in and bounces off a primary mirror at the back of the telescope, which is 32 inches across or 0.8 meters. It then gets reflected back out towards the front of the telescope. But we have a secondary mirror that's about a foot across up at the top end, which reflects the light back again through a hole in the center of the primary mirror, which then gets reflected off one more mirror, one final time, to go into either an eyepiece if we're looking at something in person, or one of our various instruments like we will be doing tonight. You can also see.
Spoiler alert.
Yeah.
Go ahead. I was trying to look at the dome briefly, just to see what's going on. It says it's in motion, so at least it knows it's spinning. Okay. Go ahead.
No problem. As you can see in the top right, it's the control room on the roof of Research Hall. Now, nobody's actually in there right now. We're all connected remotely. We're actually looking at the view of the desktop on the very far left-hand side of that camera view. And prior to the pandemic, this is where a lot of students and researchers would spend long nights in order to do observing with the campus telescope. But due to COVID-19, previous plans were definitely, I guess, accelerated such that we're now able to log into it and use the campus telescope fully remotely. And
it looks like our bottom left camera view is frozen about a minute ago, but nicely captures the view through the opening in the dome, so you can see for scale the telescope inside. And it looks like there's a light in there. It's the webcam light shining on the telescope. It's a night vision, so it's rather than what your eyes would see, but our camera's picking up the light from the other camera.
That's right. And then lastly, in case anyone's curious, the bottom right view is a view of one of the two motors that actually turn the telescope. As you can see, there's another similar motor on the side of the actual telescope body there. And so it's sitting in this fork that can twist around its axis or also point the telescope kind of up and down into the sky. And between those two axes of motion, we can point pretty much anywhere in the sky. This whole installation was put in 2011 with various upgrades over all of the years up until now, totaling a good ways over $500,000 total, I think, and counting at this point. And
why don't we take a break now, Kevin, for another question for our speaker?
Sure.
We'll just it's a good place to take a break, and then we'll move on to showing the camera views with what the telescope's looking at. In the meantime, it looks like one of our cameras has dropped out, which does happen. Hopefully it'll come back. Okay, so the next question we have for our speaker is, do they think there are any ocean worlds that are solely composed of liquid water?
Yeah, I was actually answering questions in the chat, so whoops,
Oh, you already got that one. Okay.
No, got a bit of. I'm fine to say the answer online though. So the answer is that I do not know of any worlds in our solar system that are just liquid. what's kind of cool to imagine, so funny story is that anytime we're trying to figure out the proper shape of a planet, we always have to assume it's in something called hydrostatic equilibrium, which actually forces us to imagine that, this world is liquid, and if it's a spinning ball of liquid, then it should bulge out around its equator. And that's actually an important parameter for studying the shape and the sphericity, or how spherical an object is, of these different planets. And so people who are geodesists, they really like that. That all being said, I do not know of any purely liquid planet. I don't think it is physically possible, because I think if there is liquid exposed to the vacuum of space, then all of that liquid would just evaporate into the vacuum, because there's no pressure holding it down. The reason we have liquid water on the surface here is because we have the atmosphere to protect us. So no atmosphere, no liquid water on the surface, or very little for a very limited amount of time.
Great. Okay, Kevin, thank you for that answer. And I guess, have you answered all the other questions in the chat, or is there one new one?
There are a couple that I didn't get to, and I did see a new one from Aiden. So
go ahead, we'll take that one.
Okay, so this new one.
Then we'll go back to Kevin.
So Aiden has a lot of questions. Thank you for being so engaged. So is the moon, I'm assuming Earth's moon, you mean? Is Earth's moon active, or has it stopped being active? Depends on what you mean by active, because sometimes it gets hit with an object like a very small meteor, and it actually sends seismic waves through the moon. And the moon does have a core. We actually know that because different Apollo missions actually put seismometers down on the surface. So in that way, it's still kind of active. Like, there are still some seismic signals being off. We're not actually measuring those anymore, but that activity is happening. But I think what you actually want to know about is if it's volcanically active, and the answer is no, it is not. It is pretty much stopped at this point. I don't know off the top of my head when the last eruption is thought to have happened, but do we know why it stopped? The moon is so small that it lost a lot of heat. Things that are small lose heat faster than things that are larger, and it has to do with the ratio of surface area to volume. So that's a 1/r relationship, roughly, with some extra terms thrown in. So things that are smaller will lose heat more quickly than larger objects. Throw that in with the fact that something like the moon would have had less radioactive elements to begin with. It would have had less heat to generate in the first place when compared to something like the Earth. So that is, it stopped because there's just no more heat, and there's no more heat because it's smaller, and it just ran out of things like uranium to decay.
Wild. Yeah, there was an interesting paper. I don't really remember the contents, but I remember being fascinated by it, right? Because the moon has all these lava fields on the near side, but on the far side it doesn't. And Jason Wright at Penn State wrote a paper on that a number of years ago, whether it's him or one of his students that he was working with at the time. But that's a neat mystery. Okay, so let's go back to Kevin. Looks like our camera is on the telescope is trying to come back, but Kevin, let's take us to some views of the night sky.
Yeah, sure thing. So here we're actually going to pull up the image from our CCD camera, which we use for research observing and astrophotography. And I'll go ahead and say now, because I'm sure some of the members of the audience from Dr. Park's class will want to know, the field of view is about 26 arc minutes. And as for what we're actually looking at in the CCD, I'm actually going to turn it over to Andrew to tell you about the Orion Nebula.
Hello, everyone. Sorry, it just wouldn't unmute for a second. So here we have an image of the Orion Nebula. And this was taken in, as you can see, the filter wheel, it says hydrogen alpha. So hydrogen alpha is actually a very specific red spectrum light that's emitted by stars. And it's able to be picked up very easily by, that spectrum of light is very easy to be picked up coming from stars, especially from nebulas and things like that. So this is one of the brightest nebula visible to the naked eye. It's able to be seen closer to DC, I believe. I'm not sure 100% exactly the area, but it's one of the closer nebulas that are also quite large enough to be seen with the naked eye. And it's about 1,300 light years away. So that is actually the delay in the time that you're seeing the light from the nebula when it reaches your eye. Nothing in space is really live. There is a delay by the amount of light years that it is away from you, just because space is so spacious and large. But this nebula is quite large. Oh yes, Vincent, this is a nebula. So it's 24 light years across, but despite that, it only has about 2,000 times the mass of the sun. That's because all the gases are spread out. And that gas is mostly made out of doubly ionized oxygen, which would have a blue and green color. But usually images you see of nebulas and other objects very far away, dust objects and nebulas are usually recolored. That's because we take the images in different spectrums of light, such as red, infrared, hydrogen alpha in this case, and then re-represented with other colors to show you what elements they're made of. But this one would have a blue or green color, and usually enhanced too, especially if you look at images of it online. As you can see, I believe, Kevin, are you trying to resolve the image?
I'm just giving
That's
some
not me
different
right now.
views. I'm just giving some different views. Go ahead.
Okay, so there's actually 4 bright stars in the middle part. It's called the trapezium open cluster. So there's a lot of saturation and it's difficult to see, but there are relatively young, very large giant stars towards the center, which are mostly mostly white and blue giants around that range. So those type of stars, unlike our yellow star or even red dwarfs on the extreme opposite end of what these stars are, only live a few dozen to a few 100 million years and then go supernova. So they burn through fuel relatively quickly, very large, volatile, and burn through fuel very fast. But those are the ones that are forming, and we can kind of see it right there. There are these large blobs towards the center.
Yeah, yeah. Oh, Rob, you can. Oh, he's gonna. Okay, never mind. That's something else Rob was saying in the chat. Okay, great. Thank you, Andrew.
Yep.
So let's see. So do you have anything? Let's go ahead and zoom out here. And yeah, we can actually change the screen stretch to, I believe, a uniform stretch, and then it gets a little bit easier to see what's going on with the trapezium, the 4 stars at the very center. But actually, that's not working now. Okay, so we're going to go ahead and take another question. And then if you have any questions, please ask your questions in the chat. In the meantime, I'll take the chair's privilege to ask Dr. Noviello a question, which is one thing that's always kind of fascinated me, and you've touched upon this in your talk, is that red stuff on the surface of Europa. Why red? And you mentioned that it's a salt, and it's just absolutely surprising to me about whether that could be biological in origin, or it seems like a big stretch to make such a claim, but what is going on there?
Dr. Plavchan, that is an excellent question. I'm so glad you asked it. So we think it is salt, and well, okay. The picture that I showed you did have enhanced color. If we actually went to Europa and we looked at it, it would not appear as red as it did in that picture. That was an image that was let out for just public use, not for scientific use. But it is true that the salt that we see on the surface of Europa has a reddish tint to it. And that is a clue for what kinds of chemical bonds are actually in that salt. So of course there are different, every molecule can absorb different wavelengths and it emits different wavelengths. And so what we see as the slightly red emission is a clue to how much energy this molecule is absorbing, which is a clue to what it actually is made out of. So we can look at the different light the different light beams that come out, and we can look at where there are absorption bands and try and figure out, based on those absorption bands, what molecules they actually are. Turns out that it's not like, oh, look at it and it's exactly this and that, and then we're done. It turns out there's a lot of overlap between some of these bands, so it's led to a lot of controversy. But part of the reason these bands are red at all is because of the high radiation environment that is present around Jupiter. So Jupiter has an incredibly active magnetic field. It is so toxic that, and I'm not joking when I say this, that if you were to stand on the surface of Europa and you had no protection from this radiation whatsoever, you would be dead in 3 seconds. It is incredibly harmful, and it's toxic. But what it does is all of that radiation actually changes the molecular structure of some of this salt material. So not by too much, I think. I'm actually not an expert on exactly what happens, but the radiation is actually changing what is at the surface, and it's making it more redder over time. And that's an interesting clue. So, but it is salt. We have images from Galileo, which is the mission that went and orbited around Jupiter, and it got a lot of pictures of Europa. We look at the NIMS data, which is the near infrared mapping spectrometer. Looking at that is how we get those spectral bands back from the surface. It's how we know that there's salt there. It's how we know that the salt is absorbing, or it's emitting more red, so it's absorbing a lot of the other colors. And we'd like to know more about what it is. So we're going back with the Europa Clipper, and we're going to look at it with a much higher spectral resolution and hopefully get a lot of different answers. But the reason, part of the reason is actually that Io is just belching out a whole lot of sulfur and it's ending up on Europa, and the other half is the radiation environment at Jupiter.
Wonderful. Thank you for that. I didn't even know. 3 seconds, huh? So what was that movie where there was some movie where some astronauts landed on Europa, some kind of horror sci-fi? And
so, I can think of a couple. Of course, there's Arthur C. Clarke, 2001. Yes, but Dr. Parks is right, the Europa Report. And I have seen that movie. It gave me a headache because everything was so blue tinted, and it was just blue tint for 2 hours. It was very hard to look at. But yes, and it, spoiler alert, in case anybody wants to see this movie, but everybody dies. And they're killed by a squid animal of some kind that is breaking through the ice. I will say that as a Europa scientist, I don't know if there's any place where the ice is that thin that a giant squid could fit through it to hunt. It seems kind of inefficient to wait for something to come to the surface to eat that. You would think that most of the food would be below the surface, but I'm not going to tell the giant squid what to do. I'm just going to say it was a sci-fi movie. We did not watch it. For the record, I did watch it with a whole bunch of my planetary geology grad student friends. We were watching to be entertained, but we did have a lot of fun making fun of the movie.
So it sounds like the real horror story, though, is the radiation from Jupiter's environment would kill you in 3 seconds. Holy cow, that's awful. Okay,
it's so toxic that missions that go to the Jupiter system, they have to carry so much radiation shielding. It's actually most of the mass of these missions is just that shielding.
Wild. I did not fully appreciate that. Thank you. So we are looking now at a live view of our virtual night sky. This is our telescope controller. It's called the SkyX. And so we have like a virtual horizon here, and you can see the orange things are something we call our pointing solution. But you can see the constellation of Orion. We were just previously looking at the Orion Nebula down in the sword of Orion. We're now going to zoom in on one of the stars. Spoiler alert, you probably already saw it, but we're actually going to zoom in on the Horsehead Nebula, which is a favorite astronomical photograph. Now, this is a view. I don't know if this is a Hubble Space Telescope image being superimposed here on this virtual sky, but here's a live view of the Horsehead Nebula. Andrew, do you want to say a few words about that if you have anything? I don't know if we have things to talk about on this one. If not, I can say some things. Okay, maybe we lost Andrew. So this is the Horsehead Nebula, which is you often see in astrophotography images. So this is a live view, and it looks like a grainy image with lots of noise in it, like you might see on an old TV set. Although I'm guessing most people on this call don't even know what I'm talking about in that regard. But what we're seeing here is a dark region off to the left, and we have a brighter region emitting light here, and we're seeing in silhouette a nebula, kind of similar to what we were seeing before with the Orion Nebula. This is all part of what is known as the Orion star forming region. So it's about a similar distance of around 1,200, 1,300 light years away. But we're actually seeing light reflecting off of, actually, no, this is light emitting from the gas here. So there's a hydrogen gas wall here, and we're seeing it being it's silhouetting this denser gas here. And specifically, we're looking at this wavelength called hydrogen alpha, which is numerically 656.3 nanometers. But it's basically red light. And why red light? That's the light that hydrogen likes to shine at. So this is telling us that we have hydrogen gas glowing and illuminating this denser nebula in the shape of a horse's head. As you can see here, a much longer, zoomed out, a much longer exposure taken with a bigger telescope and a little bit less light pollution. So one of the things that you might have seen me doing earlier is I could drag around these little triangles here and change how the Horsehead Nebula looks on the screen. So I wanted to explain a little bit about what I'm doing here. It's not magic, but when we take a digital picture, whether it's with our cell phone or a camera on the telescope, we are counting photons. And so we have to decide how we map the number of photons each pixel records into an intensity on the screen. And so by dragging these sliders around, that's what I'm doing. I'm mapping it from grayscale from black to white. Now this is a monochrome picture. Your cell phones will have little red, green, and blue filters on every fourth pixel, and then it will make a color composite image, but they're basically hiding all of this in the software of the cell phone to make the pictures that you look at. So astronomers, they don't really care about how the picture looks in the end most of the time. They just want to be able to bring out the details. So we map the number of photons we've counted in each individual pixel into a count on the screen. Okay, the overachieving squid, Dr. Park said. All right, thanks. So we have one more target we'd really like to look at for you tonight. And there's a nice zoomed in view of the Horsehead Nebula. This is a 2-minute exposure. Just to tell you a little bit briefly about why the telescope can see this and why your eyes can't. Well, first, the telescope's eye, the digital camera, doesn't blink. So it sits there for 2 minutes, letting the very slow rate of photons hit it. If I hover over some of these pixels, there's usually less than 100 pixels, photons hitting each one of these pixels. The number at the bottom there says 1,000, but some of that is just the background level on the detector. You can see it's just slightly dimmer and then slightly brighter on either side of that edge of that nebula. But in any event, the other aspect, of course, is that the telescope collects light like a light bucket, and it's a lot bigger than your eye. So the fact that you have a bigger eye and then it doesn't blink, it allows you to see things that are a lot fainter in the night sky than you can with your eye. So next, what we're going to do is we're going to go to a fun target, which is not natural at all. It is actually human-made in the night sky right now. JWST, the James Webb Space Telescope, which recently launched in December 25th on Christmas morning, just recently. And Dr. Noviello, you mentioned JWST in your talk on what kind of role that might play in the future study of your research. Can you tell us a little bit more about that while I move the telescope over to search for that satellite up in space?
So unfortunately, I got to Goddard a little too late to be involved with anything directly with the JWST, but I was able to watch it launch, and I know the basic information about it. I don't know if you had specific questions I can talk about where it is. It's around the L2, which is one of the Lagrange points. Lagrange points are points of stability with respect to different gravitational sources, which are really just planetary bodies in the sun in the solar system. So L2 is one of the unstable points. It means that it's kind of orbiting this one point, and eventually it's going to just go off into space and never come back. L4 and L5 are the stable Lagrangian points. So that part I actually think is a really cool part, is how people figure out the different orbits and when the engines get turned on and turned off, and how everything has to be so precise. I think orbits are just absolutely fascinating things. But in terms of the targets of James Webb, the first targets that James Webb are going to look at are ones that we've seen before with other telescopes. And the reason that has to happen, which won't happen until something like June, the reason that has to happen is we have to know exactly how these targets are going to look with or through James Webb's eyes, I guess, for lack of a better word, through James Webb's lenses. There we go. So we're going to look at some of those. I think those have already been picked out. I do not remember off the top of my head what they are, though. So after that, it's actually people are submitting proposals now to look at different objects within the solar system and outside of the solar system with James Webb. It's very competitive. It's a very powerful telescope. So it's very competitive, and anytime it's looking at something, it's not looking at something else, which is, so we might always be missing something. But I do know of at least one person who's putting in a proposal to use James Webb to look at Charon. So I wonder what we would see if we looked at Charon with its very powerful infrared imaging capabilities.
Cool, thanks. So we are there. So it is fascinating to know that the JWST is about 1 million miles away from the Earth right now. It's about the size of a tennis court. In order to do a lot of the science that Dr. Noviello talked about, it has to be very cold. That's actually one of the reasons it flew so far away from the Earth. So it deployed these things called sun shields to block the sunlight from the telescope to get the telescope nice and cold. And why cold? Well, we're looking at wavelengths of light that are redder than red, which we call infrared radiation, which is effectively heat. This telescope is designed to see the heat of the universe. That's why it's looking for some of the first galaxies and first stars in our universe. These wavelengths are great for doing that, among the many other science cases JWST will pursue. But interestingly enough, this sun shield is the size of a tennis court, and it's designed to reflect the sunlight away. It actually means we can see it 1 million miles away. So one of the things we just had a fun little telescope defect. I'm going to take one more exposure. So one of the things we've been doing since JWST is launched is we've actually used GMU Observatory to watch it on its way over to L2. And I could open up a web browser and go to Twitter and show you one of our videos while we're waiting for this exposure to take place, because I didn't have this queued up ready to go. Let's go here. There's me and my family. Let's see, where is it? It's pinned. I just scrolling too fast. There it is. So we can actually make this a little bit bigger. Here is a video of JWST on its way to L2. This was taken a couple weeks ago, and you're probably not getting the full effect on Zoom right now. It's a little bit hard to see, but I'll trace it with my mouse. But one of the things you might notice is that it glints, it brightens at different points during the time we were watching it. There's a big bright spike there, another one there, and then one more right there. In other words, JWST is sparkling like a diamond. As it turns out, one of the things they told us is that on its way, so this was taken with our observatory, this is about 3 hours worth of data. Every 6 hours it spins around, and that was helping to distribute the thermal effects and also to help with the angular momentum management. Basically, it's a spacecraft and they don't want it spinning out of control, so they spin it in a controlled way. So coming back to this view, let's see if we can find it. Now, tonight it's a little bit, it's going to be a little bit harder to see. It's not, that was 3 hours worth of data, but we can see kind of a view of the star field that we're looking at virtually. I'm just going to zoom out again and take a quick look at our orientation. Yeah, so in the case of this viewpoint, whoops, too far. Up is this way in the image. And if we put this side by side with our camera view, we should be looking at the stars. And indeed, we have this star here, and this star here, and this star here, matches this star here, this star here, and this star here. Then we have these two stars over here, matching these two stars over here. Trust me, I've been doing this a long time, so I can pattern match stars pretty quickly on the fly. But JWST should be somewhere right around here. And I'm going to zoom in on it and see if we can pick it out moving. So I'm just going to work a little bit on this. So we see a little bit more here. We see these two stars match these two stars, and we have this star here matches this star here. So it's possible that this little dot right here is JWST. It's a little bit hard to tell, but let's see if it moves. Let's take another exposure. And it moves because it's orbiting the sun. And so we're seeing this something called a parallax effect. And so we're going to see if this little dot in the night sky moves in about 50 seconds. And I think this might be JWST, just quickly kind of eyeballing it. And Kevin, soon to be doctor in a couple of years, I hope. Collins is conferring that he thinks it might be JWST 2 as well. So we're going to look very carefully. Hopefully the telescope is behaving nicely, but we'll see if it moves from one frame to the next. Fingers crossed. Yeah, it's kind of neat to be able to point a telescope in the sky and watch another telescope in space 1 million miles away. And we're looking at basically the underside of the telescope reflecting sunlight back towards us. Give it a few more seconds. Fingers crossed the telescope stayed nice and steady for this exposure. Sometimes it doesn't. Here we go. It's a little hard to tell because all the stars move too. So one of the things we could do is I could save this image. I'm just going to stick it someplace easy for now. You can see all our hard drives here. Let me go ahead and just make a new folder for tonight in our data sets here. Welcome to the 26th month of 2020. I'll make a new folder. I'll show you a trick about how astronomers detect things moving in the night sky. Easier said than done, but let's go ahead and I guess put it in here. Then we're going to take another exposure and I'm going to go over here to this tool we have, and I'm going to, after this exposure is done, I'm going to go ahead and import the two, and we're going to blink them back and forth. But we're going to put the mouse cursor on it this time. We'll see if it moves. Unfortunately, the telescope pointing is a little bit unstable tonight, so it's gonna move again. But I'm pretty sure this is it. And let's see if it moves outside the cursor. But then we also have to keep in mind that the other stars may drift as well. But while we're waiting for this one, let's give Dr. Noviello a round of applause. Again, virtual reactions, you can applaud and thank her for joining us tonight. It's been a wonderful talk, and we'll wrap up soon. I learned something today. I learned that I would die on Europa. I don't know how I didn't know that. I guess I just conveniently wanted to forget about that because Europa is so cool.
It is pretty cool. One might even say the coolest.
Yeah, so it's a little bit hard to tell if it was moving there, but I'm pretty sure that is JW. Let me go ahead and save this image and we'll blink the two back and forth. And hopefully we'll get lucky and we'll see it move. It does move pretty slowly from minute to minute. Like I said, that video I showed you earlier was when it was on its way to L2, and now it's there, so it's moving at a different angular rate on the sky. Why is that? Oh, come on, what's going on here? Okay, it's taking a while to read the hard drive. It's got to wake up the hard drive. I hope I didn't crash it. Sure, there we go. There we go. Okay. So I'm just going to bring these two images in. Only two. And I'm going to go ahead and zoom in on where I think JWST is. I could be wrong, of course. We're going to go ahead and blink these. We'll see all the stars move a little bit because of the fact that the telescope pointing is a little bit off, but JWST should move differently than what we think, what the stars are doing. At the moment, we think this is JWST, but it's a little bit hard to tell, unfortunately. So in any event, you'll have to take my word for it. We think we got it. Let's give it a little bit longer here. And we'll give it one more exposure and we'll call it a night. All right, well, thanks everyone for joining. And I hope you had a good show tonight. And we welcome you back in 2 weeks to come back and join us for our speaker in 2 weeks. Kevin, do you know who our speaker is in 2 weeks? Actually, Dr. Parks does, if he wants to tell us about our speaker in 2 weeks. We have a hand up from Hannah. You want to ask your question?
Yes. Hi. Hello. I'm sorry. Could you go over real quick what the field of view, the eyepiece was, like the CCD camera used to view the object?
Yes, we did go over that earlier. Kevin, I'll turn that over to you.
Thank you.
Yeah, it's about 26 arc minutes across, which is just a little under half a degree. And also to answer the other question you asked, our next speaker on February 15th is Dr. Courtney Crawford from Louisiana State University. I don't remember what her talk is going to be about, though.
Courtney is actually a friend of mine when I was working at Louisiana State. She is, technically speaking, currently a proto-doctor. She is getting her PhD this semester and is currently going through the whole job searching program or job searching rigmarole. She will be more than likely talking about her specialty, which is super red supergiants, specifically pulsating red supergiants.
Great. Not call me crazy, but I do think it's moved. So if we were to wait, if you wanted to wait around an hour, we could confirm it. But pretty sure that is James Webb. And I'd like to thank everyone again for coming tonight. Have a wonderful night. Keep looking up. Try to avoid the light pollution. If you have a telescope, go about an hour west of DC. There's some great night sky. Hannah, you raised your hand again. Go ahead.
Oh, no, I'm so sorry. I hit that by mistake. Have a good night.
Okay. All right. Take care, everyone. Thanks for joining us and come visit us and see you in 2 weeks. Good night. Thank you, Dr. Noviello. We really appreciate you joining us tonight. That was an excellent talk.
I'm so glad to have been here. This was a lot of fun. Thank you.